So it's really you know, very appropriate panel we have for this, you know, approaching this from various points of view. So there's Yael Kalai from Microsoft Research. Yael has been on this, actually all three have been on panels before, but I'll just do a brief introduction. Yael, of course, has a lot of work on delegated computation and interactive proofs for muggles, etc. Vinod is at MIT, and he's worked extensively on LWE, leakage resilience, and other things. Actually, Yael and Vinod recently had this very nice paper on quantum advantage from any non-local game. And then we have Thomas Vidick from Caltech, you know, who's worked on almost every aspect of this that you can think of, from verifiable proofs of quantumness to certifiable randomness and MIT star equal to RE. So it would be great to hear. Okay, so I think there were a lot of very nice ideas in what Mark was speaking about, both from the point of view of proofs of quantumness and certifiable randomness, and you know, teasing apart just you know, where these ideas go, but also just in terms of, you know, it's teasing out this piece from maybe going back to Regev, but this nice algorithmic piece that we can just view as pure algorithms. So you know, I'd love to hear what each of you has to say about this to begin with.
Maybe I'll start since I haven't spoken yet. So thanks, Mark, for the great talk. Maybe even more for the great result. Sorry, I think there's something wrong with my audio. Okay. Okay, so maybe I'll keep it short. Okay, one thing that that I realized when you were talking is fascinating is that we now have a way to set some kind of a benchmark for you know, quantum computational advantage or something. So you can fix SHA, as you said, and you could just fix a code, and you can have different sizes maybe for the code. And that's it, right? The first person who produces a string that satisfies the SHA condition and that lies in the code has demonstrated that they have a quantum computer. So you can imagine a sequence of challenges like this. They'll have done even more. They'll have generated a random string. Oh God. Okay, sorry. Just one sec.
The universal problem sees in all institutions.
Sorry. Yeah, sorry, I was traveling. Okay, okay. So then I like mostly I have a lot of questions. I actually can just say a couple of questions. I don't expect them to be answered, but I'll just bring them up. So one is regarding the code. So because you titled the paper, you know, the structure, and so you focus on the random oracle, and you argued why that doesn't count as structure. And then the other side is the code, which has many requirements, and we're talking about them at the end of the talk. And kind of in the spirit of what Umesh was bringing up, I think it might be worth trying to bring these down as much as possible and understand what exactly is needed. You know, maybe forget about codes, maybe just talk about a function or a subspace or something, and what are, I don't know if it's possible to think about it geometrically. So in terms of Regev reduction, there's some very nice geometric pictures that you can draw. And you tried the same for the code, but somehow it was, I felt that the intuition was not, or at least I didn't get it. So I thought that might be something interesting to look at. And then I want to pick up, so the randomness part. So I probably you thought about this. So I find that part slightly unsatisfactory in the sense that because of the Aronson and Baynes conjecture. So so what you give is really a generic argument that says that if you have a proof of quantumness, non-interactive like you describe it, okay, not completely generic, but almost generic, and the Aronson and Baynes conjecture is true, then you can transform it into a non-interactive proof of randomness, at least, you know, for the right kinds of adversaries. Right. But you know, you really don't want, or I think you don't want to use that conjecture, and so certainly, it would be good to try to figure out if for the particular problem that you look at, you can. So I guess because you acquiesced, I guess you this is something you tried maybe, and it just didn't work out.
Yeah, I mean, I wouldn't say that we tried super hard, but yeah, it wasn't obvious to us how to remove the conjecture, or even how to like approach the problem in a way that didn't involve resolving the conjecture.
And then beyond that, then the last thing I'll say maybe is it's you. For the other protocol, like the things that we worked on with Umesh and some other protocols, you have a whole hierarchy of things that you can do, starting from the proof of quantumness, including sometimes in the random oracle. So for example, this paper with Zvika, who I saw here, and Venkata Kopula, where we analyze the protocol in random oracle, and there's a public key assumption. But we can say a little bit more things. We can say a proof of quantumness, we can say randomness, we can also analyze quantum provers in the quantum random oracle model and argue that they must have prepared the correct kind of states, etc. And then you can build up. And so I thought that's really something that would be interesting to look at moving forward from what you did. If you can also understand what the quantum prover does and start putting your hands on that. Okay, so I'll pass it along, and then we can circle back. Okay. I think.
Actually, sorry. Before we move on, in terms of looking into what the quantum prover is doing and constraining the quantum prover. So, what's the handle into that one might look for here? Is that clear even?
I don't know actually. Basically, like proving classical hardness, we can do by drawing this connection to the coding problem. Everything becomes much harder quantumly, though.
Right. So one thing you could try, so that they must have created exponentially many points somehow, because otherwise you run into the classical lower bound.
Yes.
So that's already something. So you might be able to say,
sure.
Okay, they have some large, in the 2-to-1 examples, this is what you say. You say they must have created 2 points, but they couldn't have done it sequentially, otherwise they would have broken the problem, and so they have a superposition, and so they.
Right.
Yeah.
Okay, sorry. We should think about this offline. Yael, you wanted to.
I wanted to actually talk a little more high level about this area that your work lies in, and to understand what are, I guess, organized, because in my head it's a bit of a messy area in this. I mean, all the results are beautiful, but kind of putting them together, understanding the benefits of each one is a bit mess in my head in the following sense. So, you want to essentially separate quantum and classical in a verifiable way. You want to verify that a quantum computer is doing something the classical prover cannot. And now there's many things. There's one, it seems like the one you're focusing today is the assumptions. You want minimal assumptions or some non-structured assumptions. One is, are you doing interactive versus non-interactive? Is your like an NP, like you give in your talk, versus like an interactive solutions, like in the work of, Zvika, Umesh, Tomal, this, I don't remember all the initials, but, the first kind of paper on this. Or not the first, but okay. Then there's a question of lately. There's been I've seen papers talking about simplicity. They want it to be as easy as possible on the quantum computer so that you can actually demonstrate it. So yes. I feel like there's many axes that people are interested in, and I wondered how should we think of what are the what are the actual things we should, someone who's comes to this area, or wants to talk, to do research in this. What are the important axes? What are the less important? Are they all equally important?
I mean, I think that's sort of a central question in computer science generally, right? We face this kind of the same thing in crypto generally, where there's important questions in theory that are sort of far removed from practice. There's the important practical questions. Maybe in crypto we have efficient protocols now, so maybe the achieving faster protocols is less important. But I guess I would be of the position that they're all important questions. We want to understand the assumptions better. We want to understand whether we can, do it on, noisy quantum computers. We want to understand if it's relevant for NP problems or just interactive problems. I think these are all very important questions.
Okay, so for example, if one could do, let's say, use interaction, but to get like a separation using symmetric cryptography, then you would be, are you going to be thrilled? You know what I mean?
You mean like based on one-way functions or something, as opposed to needing an oracle?
Exactly.
Right. I think that would be a very neat result.
Okay.
Although you could argue about the interaction, right? I mean, one thing that I really like in Mark's result is that, like, from the point of view of doing an experiment or a demonstration, interaction is hard experimentally, and also you kind of need to be there, right? You need to see it in action, and so that's some kind of trust that you're placing. The sampling experiments and the thing that Mark presented, the fact that they don't have interaction and that axis. So I agree with you. There's many different axes, and you have to decide which ones you favor. But in the axis of kind of practicality or demonstrations, then interaction is a bit of a loss. But then it would be good in the axis of assumptions, like you were saying, just private key and that.
So Mark, actually, following up on what Yael was asking, is if if you wanted to replace the random oracle with a specific function, is it plausible that there would be a hardness proof, under some assumption, right? So under some standardized assumption.
I don't think so, actually. And the reason is that, the way we prove security in cryptography is by a reduction, and our reductions usually treat the adversary as a black box and kind of ignore the computational model. So there is an exception, which is when you have interaction. And this is sort of exactly where the LWE proof of quantum is, why it's interactive and why it works. But if you're in the non-interactive setting, basically our proof techniques that we have don't care whether the adversary is classical or quantum. So if you had a proof of security for classical adversaries, it would also work for quantum adversaries. So basically, it means that you need to start from a problem that's anyway, classically hard, but quantum easy.
Sorry, we can't hear you with that. Yeah.
So Umesh read my mind. This is exactly the question I had for you. So you're saying, if suppose there is a proof that is an instantiation of the oracle, let's say SHA, and a proof that if the classical algorithm succeeds, then you find collisions in SHA, right? And you're saying that means you have a quantum algorithm to find collisions in SHA.
At least using the techniques that we have. Maybe there could be some crazy proof that makes non-black box use of the algorithm.
Right, but reductions. Let's say black box reductions for a moment.
Yes.
So it comes across to me that in a funny way, your result is a random oracle uninstantiability result in this sort of weird sense, right?
In a way, yes.
Except it could be that you can instantiate this oracle under the hardness of factoring, and there is no contradiction, right? I mean, you would get a factoring algorithm, but then you could ask, okay, why are you doing any better than actually asking the quantum computer to factor numbers, right? But imagine the following possibility, and I want to know what you think. Let's say the reduction from solving this problem classically to factoring to solving this problem classically is adaptive. It makes many queries to the oracle. It's a huge number of queries to the oracle. Then you would get a quantum algorithm for factoring that invokes this oracle many, many times. Right. So it would be a circuit for factoring, which uses like n times this oracle, and perhaps this is just as big as Shor's circuit, which is size n squared or something like that, n squared and cubed or something like that, right? But the classical algorithm, the quantum algorithm that actually solves this problem, right? That's what you're plugging in. could actually be much smaller than the short circuit. Am I making sense? So you could actually achieve quantum completeness using a circuit that is a lot smaller than the short circuit and get a reduction to the hardness of factoring while, not breaking any barriers.
I see.
I mean, that would be a better demonstration of quantumness, and this better than actually asking the quantum computer to factor, because it would be a smaller circuit somehow.
I mean, yeah, that's a possibility. I don't have any guess as to if that's likely or not, but
fair enough.
Guess, yeah.
But sort of, it comes across as strange to me that you cannot possibly instantiate this oracle and come up with a proof under LWE or SHA, unless these problems are themselves quantumly easy. But somehow you have to find an instantiation based on the hardness of factoring.
Right.
Very odd. Very odd to me.
Certainly.
Makes the result even more intriguing.
Yeah.
And I guess I'll just say, since it was not exactly brought up, but in terms of like actual practical demonstrations of quantum advantage, it's unclear if our construction makes any progress there. The tools are classically very efficient, right? It's basically list decoding algorithms and hash function evaluations, but I think even that is sort of like hopelessly beyond the scale of current noisy quantum computers. Even just the hash function, I didn't do a deep dive into the literature, but what I could pull up seems to say that even evaluating SHA requires hundreds of thousands of quantum gates.
But you don't need SHA, right? I mean, you could.
Right. So there's potentially room for improvement there. The thing I'm more concerned about is the decoding algorithm. While not necessarily too inefficient, you have to solve some big linear system, and then you have to the solution corresponds to a polynomial that you then have to factor. Like these things, I'm not an expert in implementing classical algorithms as quantum circuits, but they strike me as things that are, very sensitive to noise and, unlikely to be, easily implemented. But who knows?
Can I ask a question?
Oh, yes, please.
Yeah.
So you're saying that to implement SHA by quantum circuit would be kind of stupid because it would be much more inefficient than doing it classically. Is there a proposal out there for a hash function, which is the kind that was easy to implement or nicer to implement on the quantum circuits and still seems to avoid, in the same way the SHA is, not because it's based on some nice algebraic problem or geometric, but because of some set of principles that people have come up with, like they did when they did with SHA?
Yeah, I'm not aware of any. I mean, I guess the motivation has maybe not been there. In general, you would like it if your hash functions couldn't be implemented on a quantum computer, so that you can't run Grover's algorithm.
No, the motivation is that if you want to do post-quantum cryptography, you want a hash function.
But if it's post, right? Yeah, certainly. Look, if you want to implement your cryptography on a quantum computer, you'll need a compatible hash function. But right now, we're sort of generally more worried about the cryptography that's running on our classical computers and whether the attacker with a quantum computer can break it. And there's just a lot less motivation to design a hash function that's compatible with the quantum computer. But the short answer is no. I don't know if anyone has tried to do this.
I think what Rafi means is not post-quantum. He means post, kind of when everyone now has a.
What we confusingly call quantum cryptography.
Understood. No, good answer. But still, I think that interestingly for classical cryptography, designing these hash functions was before public cryptography. That was the basic thing that you started with, coming up with some beast, which seems to be hard and still is a hard.
I think it's a well taken point that not for post-quantum cryptography, but for proofs of quantumness and things like this, it's a good challenge to think of hash functions which are optimized not for classical computers, but for implementation on quantum computers. Yeah.
So for example, you could think about hash functions that are computable in parallel, right? Very well think about those, Kohlrach's function and modify it somehow.
Right.
And I guess the other barrier is list decoding, right?
And I think that's the harder of the two. That'd be my guess.
Is it, again, I don't know if actually depth is, low depth kind of implementations would make it more amenable to sort of near-term demonstrations. The experts should. Yes. So then I guess the other barrier is coming up with a parallel decoder, right? List decoder. Is there a reason it should not, such a thing should not exist?
I mean, this is far outside my expertise. I mean, so the high level blueprint of these decoders, right, is you solve some system of linear equations, and then you interpret the solution as a polynomial that you then factor. And I guess it's, I actually have no idea what the the depth complexity of these algorithms is. The first step maybe could be parallelized.
Yeah, right.
But I don't know about the factoring step. No idea.
Right. But you don't necessarily need Reed-Solomon codes, right? I mean, that's just one thing that worked. For example, sort of, I don't know, LDPC codes or something that it doesn't seem like the constraints of the problem are so bad that you really are forced to look at.
Right. So yeah, there's a lot of flexibility in the in the code. You just need to ensure these two properties. It's information theoretically list recoverable, and then the dual is efficiently list decodable. And I guess the implication there also is you need a linear code.
Right. Yeah.
And yeah, so we sort of stopped when we found a code that satisfied these constraints. I'm not sure a lot of people have been motivated to find codes that have nice decoding properties in both the primal and the dual code. And so, maybe there just hasn't been a lot of literature, trying to explore such codes.
I guess they come up in quantum error correcting codes, right? You look for both. Yeah.
Yeah. So I guess, can you sort of explain where the quantum advantage here comes from? I mean, there are, in the old sort of non-local games way of thinking about it, comes from entanglement, right? And the sort of the BCMVB type things, it comes from non-rewindability, right? Can you sort of point to a sort of a feature of, quantum?
Well, I mean, I guess the way I would think about it is, so one thing you can do with a quantum computer is you can, generate a uniform superposition, and then query it on a random oracle that has 1-bit outputs and measure the result. And what you get is a uniform superposition of pre-images. Right. And maybe until recently, it wasn't clear what's the point of doing this. What does such a state have any advantage over just sampling a random classical value?
Right.
And maybe the first hint of progress was the sort of the follow-up work to the original proof of quantumness from LWE that simplified things using random oracles. And they're they're also using a 1-bit oracle, and you can sort of interpret what they showed is that in at least assuming LWE in a computational setting, you actually do get something special when you have this quantum superposition of inputs of a 1-bit random oracle.
Right.
And our result is sort of saying that in a different way.
Right. That's interesting. It's very interesting.
Right. And I guess at sort of at a low level, what's special about this quantum state is that if you apply the quantum Fourier transform, you get something that has that's concentrated around 0. Whereas if you just had a classical string and you apply the Fourier transform, you get a random string. And that's kind of like the low level, concrete feature that we take advantage of.
Right. Right.
That's really interesting. Well, if we back out even further, then it seems like in some sense, if you look at what Regev was originally trying to do was to come up with a quantum algorithm for shortest lattice vector, right? And or finding a short vector, and of course there was this one step that that he couldn't really do, and so that became LWE, right? So instead of giving an algorithm, it ended up saying that there was this hard problem, and with a quantum reduction showing that it was a hard problem. And so in a sense, what you've done is you've sort of massaged that with these new insights, as you were pointing out, and gone back to saying, well, to finishing up that goal of saying, here's something for which you can use this approach to give an efficient quantum algorithm.
Right, exactly.
It's a very nice way to put it.
Yeah, that's very nice. Yeah. Do you so there is this new algorithmic technique here, right? This multiplying quantum states. Do you see sort of other applications of it beyond sort of? I know you have all these sort of applications of for randomness generation, and down the line the questions where can you sort of do verification in general, right? Computational verification in general, but the technique itself, seems very very novel. Sort of an open-ended question.
Are you referring to the application or the abstraction of Regev, or like the particular setting with the random oracles corresponding to
let's say with the particular setting. So this is a sort of a framework, like Umesh said, to make the Oded reduction into not a reduction but an algorithm, right?
Right.
So that's a new algorithmic sort of tool in the toolkit now. Do you envision sort of applications beyond sort of the obvious, in a sense, right?
I don't know. I mean, I guess there's a question of if this could be used for name some quantum cryptographic object that people want to build. If it's or like what was mentioned earlier about actually characterizing what the quantum computer is doing as opposed to just verifying that it's quantum. So that's kind of one maybe the most natural thing to think about next. Can you do I guess what quantum protocols could something like this enable?
Mark, sort of along this line, have you thought about potential connections between this and quantum lightning? Your approach to doing quantum money, feels quite similar, right? That you have these superpositions that okay, in this case, it's clearly not money right away because any quantum computer can just generate this, but you could imagine like maybe there's like some hidden way to generate the state once, and like if I give it to you, like generated with some secret value that like maybe somebody else can't generate it again now.
Right.
Because
Yeah,
it's
so actually,
verifiable, right? So that's like the key thing that makes it
exactly
useful. Right?
So a problem that I've liked to advertise to people is sort of back in Regev's version. The question is, can you come up with a setting like Regev, but where so Regev showed that search LWE is hard if you assume sys is hard. The question is, what about decision LWE? Now, for a random linear space, search and decision are equivalent, but you could have a structured version. The Regev reduction preserves any structure, right? If your sys instance is if your particular class of sys instances is hard, you get the corresponding LWE search problem is hard. But maybe that search problem for some particular subspaces, maybe the decision problem for some particular subspace actually becomes easy. And if you had that, actually, you probably would get quantum lightning, or more specifically quantum money. Basically, the ability to do the decision the decision problem allows you to like verify. But to actually construct the state, you need the ability to do search.
And Mark, 1 second. So you're saying for random LWE with random matrices, you're saying there is a reduction from search to decision?
Yes. Yeah. Right. So we don't expect we don't expect decision LWE to be easy on a random matrix.
Okay. I see.
Right.
Okay. I see. That's what you mean.
But maybe there's a matrix that has some nice structure to it that makes the decision version easy.
Yeah.
And sort of like switching back to the topic of this paper, we showed a particular matrix, namely the ones coming from these error correcting codes, and we also changed the metric, from L2 norm to this, this Oracle thing. It's the, I guess what you would want for a quantum money, quantum lightning kind of result is something where the search problem is actually hard, because that's what you need to actually, go through the whole algorithm, but you still want the decision version to be easy so that you can still get the verification.
I see.
That's great. Any other final thoughts? Questions? Well, thanks again. Thank you, Mark, for fantastic.
Thank you for having me.
Thanks to the panel for really lovely comments. So we'll see you next week.
Amazing.
Thank you, Mark.
Thank you for
the
talk.
very nice. Thank you.